Our next topics in Chapter 6 are going beyond the percent yield to the limiting and excess reactants in a reaction mixture, the next section of the chapter and of the learning objectives. And in connection with that, we can talk about the mass of excess reactant remaining at the end of a reaction and a mass of product produced. Those are the kinds of things we need. When we're discussing these topics, we're going to have to make some definitions. The limiting reactant is a reactant which is present in a limiting amount, and how much or the extent to which a chemical reaction takes place depends on that limiting reactant. It's only going to give you as much product as that reactant allows. The excess reactant will be the other one, and sometimes there's more than one, but any of the other reactants still present that are left over after the determination of the limiting reactant. So when we do this, we're going to think in terms of stoichiometric amounts, proportions that are indicated in your old friend, the balanced equation. That's where we always have to begin. Okay, so let's do one with pictures. Not necessarily your favorite thing, but let's try it. Nitrogen monoxide reacts with oxygen to make nitrogen dioxide. And so it takes two nitrogen monoxide molecules with one oxygen molecule to make two nitrogen monoxide or nitrogen dioxide. Okay, so it's going to take two of this guy, this blue and red combination, with one of these to make the nitrogen dioxide, which is apparently this one down here, NO2. And if you look at this example, you can kind of see what's going on here. That looks like it's supposed to represent a cubical box or something that all these are bouncing around in. These are all gases. And so if you think about how many oxygens there need to be to go with the nitrogen monoxide, there should be twice as many nitrogen monoxide as there are oxygens. So in other words, pairs like this will have to combine, and two of these have to combine with the oxygen to make nitrogen dioxide twice. So let's look at that. So in this case, the nitrogen monoxide is the limiting reagent. And why is that? So if you have to have two nitrogen monoxides for every oxygen, we look at the proportion of what's available in this mixture. So we count them up. So how many nitrogen monoxides are there? 1, 2, 3, 4, 5, 6, 7. And that diagram. And how much oxygen is present. So let's count those two. 1, 2, 3, 4, 5, 6, 7. They're equal amounts, but you have to have twice as many nitrogen monoxide as oxygen to have a complete reaction. So if there's 7 of each, there isn't as much nitrogen monoxide as those oxygens would allow. So nitrogen monoxide is the limiting reagent, and as a result, oxygen is in excess. So after the reaction is complete, you will have made some of the molecules. So let's see, 1, 2, 3, 4, 5, 6, 7. They didn't count these up right. They got 8. It's not exactly pictured correctly. Sorry about that. But you only make as many nitrogen dioxide molecules as the nitrogen monoxide will allow. In other words, unless I counted wrong, if you only had 7 nitrogen atoms to start, or 7 nitrogen atoms to start with, you're only going to get 7 to end up there. And you can't get more. Ooh, sorry about that. Let me fix. Apparently the technology is not cooperating with me at all today. So you have apparently in this diagram an extra nitrogen dioxide included. You can only get as many nitrogen dioxides as you had nitrogens to begin with. But oxygen is the excess reagent. There's excess oxygen shown left over after you make nitrogen dioxide. There they are. Okay, let's look at another example. A reaction that's interesting if you're thinking about how polymers are made from things like polyester type things. Ethylene oxide is this first compound here. So ethylene oxide is shown with C2H4O. Is reacting with water to make another compound called ethylene glycol. Ethylene glycol is actually known in antifreeze as the major component of automobil antifreeze, and it's used in a lot of polyester polymers. Because water is cheap and abundant, it's going to be used readily in excess when you're putting it together with this ethylene oxide to make the product. And the point of it is, if you put in plenty of water, you should use up all of the expensive portion reagent in your mixture. So that's the object of the GIL, object of the process. So if you picture this with actual structures that make more sense of these funny names that don't mean anything to you right now, the ethylene oxide is shown on the left reacting with water to make ethylene glycol. This is a very simplistic reaction, thankfully, because one ethylene oxide reacts with one water molecule to make one ethylene glycol. And so now we're thinking about how these limiting reactants are going to be described in terms of this particular example. So if you have 3 moles of ethylene oxide and 5 moles of water, how do we figure out which one is limiting and which is present in excess? Not too tricky, but let's talk it through. So if you've got 3 moles of ethylene oxide and 5 of water, that means you can make 3 ethylene oxides combine with 3 of the water, and you will make 3 of the ethylene glycol. So you'll use up only part of them, and 3 of the water molecules can combine to make products, but 2 are left over. So the 2 extra water molecules become excess. They are unreacted. There are 2 different strategies that are suggested for determining which reagent is limiting, and we'll describe each of them, and then we'll do a couple of examples. Method number 1 is to calculate the moles of all the reactants that are provided. Following that, you calculate the amounts of all the other reagents that are needed to complete the reaction with those numbers of moles of reactants. Then you compare what actual moles are available to the needed ones, and that will reveal what is limiting. The second approach to these limiting reagent questions, limiting reactants, is to do a slightly different method, but we begin again the same way with calculating the moles of all the reactants. And then you choose a product for each reactant. Sometimes there's one, sometimes there's more than one, and calculate the amount of product formed for each reactant. So reactant 1 and 2, see how much of the certain product you can make. And then you compare the amount of product possible from each reactant amount and the least one. Whatever one comes up with the least amount of product, that is your limiting reactant, because limiting means you cannot get more than that because something isn't provided in sufficient quantity. So doing that, let's try an example with those kinds of ideas. All right, so simple reaction again of hydrogen and oxygen making water. If you have 5 moles of each reactant available, which one is limiting? Well, the picture doesn't show 5 of each, but you kind of have to think about it for a minute. If you had 5 moles of hydrogen and 5 moles of oxygen, what could you make? Let's think about it for a sec. Each of these methods requires you to begin with a number of moles, and you've been given moles in this example, so it makes it simpler. So if you have 5 moles of hydrogen, your ratio of moles in this example is 1 mole of oxygen for 2 moles of hydrogen, and in this case that would be 2.5 moles of oxygen required. Do we have 2.5 moles of oxygen? Yes, we have more than that. So that means that the oxygen is more than 2.5, all right, greater than, there's another way of saying it, greater than 2.5 moles of oxygen are present, and so oxygen is in excess. That means that the other reactant is going to be limiting, so hydrogen is the limiting reagent. We could have done the same calculation going other way with oxygen, but we didn't need the second step because we already figured it out from this one. Let's do another one. Same reaction, keeping it simple. Let's use method 1 where we find, using grams now, the moles of all the reactants and then how many moles are needed. This is the method I tend to lean towards. Now, both of them work. 50 grams of hydrogen. And with that, we're trying to determine how many moles of hydrogen are present, which we haven't done yet. So let's put in our molar mass. 1 mole of hydrogen gas is still going to be 2.02 grams of hydrogen. And that gives us an answer that is kind of a funny number. I'm writing it down here for you. but let's not get fussy. It's essentially 25 moles close enough. 25 moles of hydrogen present, mostly. If you look at 50 grams of oxygen, and again, this is an approximation is still not so bad because it'll give you the right answer without being fine-tuned in this case. 32 grams of oxygen is going to be a mole. And remember, these things always have to be set up so that the units are going to cancel. So be sure you do that. Oh my goodness, my tool is being really unhelpful today. And so the grams of oxygen cancel. Wow, sorry. And so 50 divided by 32 is clearly a lesser number. It's somewhere around 1.5. So you don't have very much oxygen compared to the hydrogen. And the moles of oxygen are very much less than the hydrogen that you would need to go with it. In other words, that would require approximately 3 moles of hydrogen, and we have way more than 3 moles available of the hydrogen. So 3 moles of hydrogen needed, and therefore the hydrogen is in excess, and the oxygen is limiting. Okay, now let's do it with the other method. If I can advance the slide would be the next step. All right, so 50 grams of each reactant available, which is limiting. And we're going to do this to find the amount of product from each. So that takes a slightly different approach. So 50 grams of hydrogen, we'll figure out how much water is going to be produced. 50 grams of oxygen, and we'll see how much water is produced. Second one, here we go. So if we have, same thing we started with before, 1 mole of hydrogen is essentially 2 grams. For this purpose, we'll be fine because this is kind of crude calculations with 50 grams. And they're vastly different in their molar masses, so we'll be okay. And again, that's essentially 25 moles of hydrogen. But then we have to figure out the moles of oxygen and the number of grams of water that are produced. So how many moles of water are formed in relationship to how many moles of hydrogen react? Go back to your balanced equation. It's 2 and 2. And so the moles of hydrogen now cancel, and we want to find out, if you stopped there, you would do that too without calculating grams. We'll just say, let's leave it there without doing the rest of the steps because moles will get us enough an answer without the grams. We're okay with that. And so that tells us that we had 50 divided by 2, which was 25, times 1. So that means you're going to get 25 moles of water, potentially, given sufficient oxygen, from 50 grams of hydrogen. The opposite calculation then, or the second way of thinking through this to determine who's limiting or what's limiting, I guess it's not who is what in these examples. And then we're going to figure out the amount of oxygen. Same way we did before. 1 mole of oxygen is 32 grams of oxygen. And this time we're looking at the mole ratio to figure out how much product is going to be resulting from this oxygen. So there's moles of oxygen goes on the bottoms where it will cancel, and relating to moles of water on the top where it will relate the two. And in this balanced equation, there's 2 moles of water, right, either one, for, in this case, 1 mole of oxygen. Now, I told you it was approximately 1.5 moles of oxygen from the first step. We calculated how many moles of oxygen times 2, so it's about 3 moles of water. And so you would get far less, and that means that the limiting reactant is apparently the oxygen. Limiting oxygen. Okay. Ooh, that was a very loud squeak. Apologies there. These feel very similar, but this is effectively what you have to do when you're thinking about limiting reagents. You have to calculate the amounts of product available, product possible, and whichever one gives you the smaller amount of product produced resulting from the process, that is going to be limiting. And again, the hydrogen is going to be in excess from this calculation because you will get, no, you would not be able to use it all to make the water in this case with a limiting amount of oxygen. All right, would you like to perhaps work your way through one more example? Maybe you wouldn't. Maybe let's try one. Lithium oxide. It's used in the space shuttle, imagine that, to remove water from the air supply according to the equation shown here. We have lithium oxide reacting with water to make lithium hydroxide. If you have 80 grams of water that need to be removed, and you have 65 grams of lithium oxide, let's hope they have enough, we'll find out what is limiting. And this is a multi-step question. We want to know what's limiting. We want to know how many grams of excess reactant remain and how much lithium hydroxide are formed. So if you follow us through, we can make all the steps of this calculation. So begin with the balanced equation. Notice that this should be balanced because you got 2 lithium on the left, 2 oxygen on the left, 2 hydrogen on the left, and you've got 2 of each on the right. So far, so good. So to figure out which is limiting, let's start by figuring out how much water will react with the 65 grams of lithium oxide present. Start with your 65 grams of lithium oxide. You determine its molar mass by taking 2 lithiums, which are approximately 7, add them to 16, and you get about the right number here, if that makes sense. Double checked, yep, that's a good molar mass for lithium oxide. Go back to the balanced equation and then determine from that how many moles of water are going to be reacting with that amount of lithium oxide. It's a 1-to-1 ratio, very simple here. And if we're doing all this correctly, the grams of lithium oxide cancel, the moles of lithium oxide cancel, and we determined how many moles of water are going to react with the amount of lithium oxide provided. Let's figure out then how much water is provided. And so we have 80 grams of water, because it's just in the question, that's the way it was stated. The molar mass of water is 18 grams for 1 mole of water, so the grams need to go on the bottom, so the grams of water can cancel. And put the numbers into your calculator, and you get an answer, and you see that 4.4 moles of water are provided. You only need this much, a smaller amount of the water, and so that means that the lithium oxide is indeed limiting. You have extra, plenty of water, it's excess in this reaction. Okay, so that was the first question. Which reactant is limiting? Lithium oxide is limiting. Now, how many grams of excess water remain? Well, if you have to go back and double check here, we had 2.17 moles of water that will react in this process. And the molar mass of water is used in this sense. Oops, there's a multiplication step that got out of line. And so the moles of water are going to cancel. And it will tell you if you started with that many 2.17 moles of water, you will end up times 18 to say that would be 39.1 grams of water consumed. You have to figure out how much was used or consumed in the process, and then from the value initially provided, in other words, 80 grams of water were available in this reaction, 39.1 were consumed, the amount that remains is 40.9. So this was the second question in this particular problem. Apologies for the tool that's leaving me lines that I wasn't intending. Sorry about that. All right, then the third part was how much lithium hydroxide is going to be formed. So lithium hydroxide is going to be based on the amount of water that was used. And if you had 2.17 moles of water, you're going to have 2 moles of lithium hydroxide for each mole of water, remembering that you're always going to set up things with conversion factors, so something's going to cancel. Starting off with the moles of water, and twice as many moles of lithium hydroxide result. Again, calculating using, this is again notably a mole ratio, and then we go to a molar mass. And the molar mass of lithium hydroxide is 23.9. The moles of lithium hydroxide cancel, and it gives you 104 grams of lithium hydroxide. That was a multi-step question that had various, oh my goodness, sorry, various aspects to it that weren't that you won't always have all of those steps in a particular question, but it's an example of how you could determine the limiting reagent, the excess reagent, and then actual yield given using the limiting reagent. Apologies for the funny squiggles that I got here. I hope these examples are helpful to you. Please use them as you work through your homework. Ask more questions as needed, and I'll see you in class.